Okay, so now basically there is a couple of things that we need to discuss about types of matrices. So there is basically the different types of matrices that we have definition wise. We have a column matrix. We have something called a column matrix. We have something called a row matrix. We have something called basically a square matrix. A square matrix. We have something called a diagonal matrix. Something called a diagonal matrix. There is something called a scalar matrix. There is something called an identity matrix. And that's about it. And there is also the zero matrix. There is also the zero matrix, right? So we will discuss these one by one. So first of all, the column matrix, is just simply a column matrix, meaning that a matrix that has only one column is called a column matrix. It doesn't matter how many rows you might have, but if you have only one column, then the matrix is called a column matrix. So for example, if you have A is equal to, for example, 0, for example, square root of 3, negative 1, and for example, 1/2, this is a column matrix. You can see that you have one column and 4 rows. This is a 4 by 1 matrix. And therefore, since you have one column, it's called a column matrix. Right? Now, in general, you can say that basically A is equal to A of ij, m times m by 1, is basically a column matrix, is a column matrix of order basically m by 1. Okay, so that's a column matrix. Now a row matrix, by the same logic, it's a matrix that has only one row. For example, if you have B is equal to, for example, negative 1/2 square root of 5, for example, 2 and 3, this is a row matrix. You have only one row and 4 columns, and therefore it's called a row matrix. In general, B is equal to B of ij. Basically, you have only one row, so 1 by n. 1 by n is so you can say that in general, B being this matrix is a row matrix, of the order basically 1 by n, right? Now a square matrix, as we have here, a square matrix is a matrix that has the same number of rows as the same number of columns. It has the same number of rows as the number of columns, or you can say it the other way around, the same number of columns as the same number of rows. Or you can say that the matrix in which basically the number of rows are equal to the number of columns is said to be a square matrix. So then basically you can say that m by n, and m by n, basically matrix is said to be square matrix, is said to be a square matrix if m is equal to n, right, and is known as a square matrix of order n, and is known as a square matrix of order n, right? So for example, if you have this matrix over here as, for example, I don't know, 3, -1, 0, 3 halves, 3 square root of 2, for example, 1, and then you have 4, 3, -1. This matrix is a square matrix. You have 3 rows and 3 columns. This is a square matrix of order 3. Now in general you can say that A is equal to basically A of ij, m times m is a square matrix, m times m is a square matrix of order m, right? Now, as a note, we can say that if A basically is a square matrix of order n, then elements are said to, the elements A11, A22, A33, all the way up to ANN are said to constitute the diagonal of the matrix A. So this is, of course, you can pay attention to this fact as well, meaning that if A is equal to a matrix A of ij, is a square matrix of order n, then elements, or you can say also entries, basically A11, A22, for example, A33, all the way up to ANN, are said to constitute the diagonal of the matrix A. Meaning that, for example, if you have this matrix A as, for example, 1, -3, you have 1, -3, 1, and 2, 4, for example, -1, and 3, 5, and 6. And if this is your matrix, of course you can see that this is a 3 by 3 matrix. It's a square matrix of order 3. Now these elements over here, so this is this element over here is, this 1 is basically A11. This element over here, this 4, is A22. And this element over here, 6, is basically A33. These elements, therefore A11, A22, and A33, constitute the constitute the diagonal of matrix A, right? And the elements of the diagonal A are basically 1, 4, and 6, basically in this case, right? Now, the next matrix that we have is a diagonal matrix. So a diagonal matrix, first of all, it has to be, I think it has to be a square matrix, otherwise it's just not possible. So, okay, so about the diagonal matrices, as I suspected, we say that basically, first of all, for a basically matrix to be diagonal, first it has to be a square matrix, otherwise you will not have the diagonal in the first place, right? So we say that a square matrix B, which is equal to, for example, B of ij with the order m by n, or I'm sorry, m by m, because it's a square matrix, is said to be a diagonal matrix, if all of its non-diagonal elements are 0. All of its non-diagonal elements are 0, right? That is a matrix B. That is a matrix B, which is equal to basically B of ij m by n, m by m, is said to be a diagonal matrix, if B of ij is equal to 0 whenever I is not equal to j, right? Meaning that whenever I is not equal to j means that whenever you're not across the diagonal, all of those elements are 0. Whenever you are across the diagonal, then it doesn't really matter whether they are 0 or not. The condition is that all of the non-diagonal elements are 0. If that's the case, then you can call it a diagonal matrix. So for example, A, which is a square matrix, as 4, having only one element, this is a square matrix of order 1. This is not a diagonal matrix because, well, it seems that this is actually considered as a diagonal matrix. Or, yes, of course, because we can assume that basically all the other elements have been 0 or probably some convention. But basically this matrix is actually a diagonal matrix, is considered as a diagonal matrix. Now I don't know what the reasoning behind that could be, but it is a diagonal matrix. Or B is -1, -1. So this is basically the diagonal in your matrix, meaning that if you write a 2 over here and 0, 0, this slanted line is the diagonal in your matrix. And across this line, it doesn't matter what you have, but all of the other elements that are not across the diagonal are supposed to be zeros, and therefore, for example, this is a diagonal matrix, and this is, as you can see, a square matrix. Or C, as you can see, is negative 1.1, 0, 0, and 0, 2, for example, 0 and 0, 0, 0, 0, 3. The diagonal of this matrix is this slanted line, and you can see that you have these zeros here, and you have these zeros here, and therefore this is a diagonal matrix, right? So, and the order of this matrix is 1. The order of this matrix is 1. The order of this matrix is 2. And the order of this matrix is 3. So that was all about the diagonal matrices. Another type of matrix that we have is called a scalar matrix. So a scalar matrix is basically, so the definition is that a diagonal matrix, and you know what a diagonal matrix is? A diagonal matrix is said to be a scalar matrix, is said to be a scalar matrix if its diagonal elements are equal. If its diagonal elements are equal, right? That is, a square matrix B, a square matrix B, which is equal to, so first of all, the matrix has to be diagonal, meaning that it has to be a square matrix, and it has to be a diagonal matrix, meaning that A of ij is supposed to be equal to 0 whenever I is not equal to j. So that makes it a diagonal matrix. That makes it a diagonal matrix, and moreover, it has to be basically all of the elements of the diagonal are supposed to be equal, meaning that A of ij is supposed to be equal to, or you can say A of ij is supposed to be equal to k. All of A of ij's are supposed to be equal to k whenever I is equal to j, meaning that across the diagonal, all of those elements are supposed to be equal to one constant k, for example. For some constant k, right? So you can say that is a square matrix B, which is equal to basically B of ij, n times n, is said to be a scalar matrix, if basically these conditions are met, meaning that first of all it has to be a square matrix, right? And then the conditions are exactly b of ij is equal to 0 whenever I is not equal to j, and basically b of ij is equal to some k whenever I is equal to j for some constant k. As an example, you can say that for example A is equal to this matrix is a scalar matrix. This is a scalar matrix because first of all it's a square matrix, and second of all it is a diagonal matrix, all the other elements except for, or basically you could just simply consider this matrix as a diagonal matrix. As I mentioned before, I do not really know what the reasoning behind that is, but I'm assuming that whenever you have a matrix that has only one element in it, you can for whatever reason you can consider that as a diagonal matrix, meaning that and the diagonal matrix basically is the kind of matrix where all of the non-diagonal elements are equal to 0. But then in this particular case you can actually consider this as a diagonal matrix, right? And it is a scalar matrix because across the diagonal all of the elements are equal to some k, and in this particular case the k is equal to 3, for example, right? Now, as another example, for example, some matrix B as -1, 0 and 0, -1, right? So this is first of all a square matrix. Second of all, it's a diagonal matrix because you have these two zeros over here. And third of all, it's a scalar matrix because all of these elements across the diagonal are equal to some k equal to -1. Or for example, this matrix C, you have square root of 3, 0, 0. You have 0 square root of 3, 0. And you have 0, 0 square root of 3. Right? So you have 0, 0 square root of 3. So in this case also, what we have is a matrix that is first of all a square matrix. Then it is a diagonal matrix because you get all of these zeros over here across, in the case of all the non-diagonal elements. So it's a diagonal matrix. And when you say diagonal matrix, it's automatically a square matrix. And then it is a scalar matrix because across the diagonal all of these elements are equal to square root of 3. So it is considered a scalar matrix. It is considered a scalar matrix, and k is equal to, for example, square root of 3, right? And these are all scalar matrices of, so you can say that A, B, and C are scalar matrices, of orders 1, 2, and 3, right? Now, there is one more type of matrix that we have, and that is called an identity matrix. That is called an identity matrix. Now, what an identity matrix is by definition is a square matrix in which elements in the diagonal are all 1 and the rest are all 0, that is called an identity matrix. So that is a square matrix. That is a square matrix in which elements in the diagonal, are all 1, and rest are all 0, and the rest of the elements are all 0. That is called an identity matrix. In other words, so when you say a square matrix in which elements in the diagonal are all 1, that automatically becomes a scalar matrix, right? Because a scalar matrix is the kind of matrix basically a scalar matrix is a diagonal matrix in which basically if the diagonal elements are all equal, right? And in the diagonal matrix, basically, of course, a diagonal matrix is a square matrix, and all of those elements which are non-diagonal are all equal to 0. Now, so you can say that if you have a scalar matrix, and if in this scalar matrix k is equal to 1, then that scalar matrix is simply called an identity matrix, right? So then you can say that in other words, the square matrix A, which is equal to A of ij n times n, is an identity matrix if basically A of ij is equal to 1, if I is equal to j, and it's equal to 0 if I is not equal to j. If I is not equal to j, then it's equal to 0. If I is equal to j, it's equal to 1. So what that means is that you will have some matrix A, and you can imagine that you have this matrix A. All of these elements are 1, 1, 0, 0, 0, 1, 0, and 0, 0, 1. And this is called an identity matrix. This is called an identity matrix, which means that whenever I is equal to j, which is across the diagonal here, whenever I is equal to j, basically A of ij is equal to 1, as you can see. And whenever I is not equal to j, which is basically these elements and these elements here, in these two cases, you can say that A of ij is equal to 0. That is called an identity matrix. So as you can see, you can say that an identity matrix, matrix is a scalar matrix in which k is equal to 1, right? So in a scalar matrix, k can take any value that you want, right? But if k is equal to 1, then that scalar matrix becomes an identity matrix. So it's very simple. So, and we have the same thing over here. It says that observe that a scalar matrix is an identity matrix when k is equal to 1. That's the same thing that we have written here. But every identity matrix is clearly a scalar matrix. Of course, every identity matrix is a scalar matrix because there is only one identity matrix after all, meaning that all identity matrices have basically a number of rows and a number of columns, and the number of rows and columns are the same because they are square matrices, but all of the elements across the diagonal are equal to 1. So that means that all of them are automatically scalar matrices. But some scalar matrices in which k is equal to 1 become identity matrices, right? So that is all about the identity matrix. Now the next thing that we have here is called a zero matrix. A zero matrix. So a zero matrix by definition is, so a matrix is said to be zero matrix. Is said to be a zero matrix or null matrix if all of its elements are 0. If all of its elements are 0. Right? So for example, this matrix is a zero matrix. This matrix is a zero matrix. This matrix is a zero matrix. This matrix is a zero matrix, and so on and so forth. And the zero matrix is denoted by O. Is denoted by O, not 0 but O. So, and the order of the zero matrix, the order of the zero matrix is clear from the context. You will know what I mean, what is meant by this statement, because basically in operations that you do on matrices, sometimes instead of actually writing the matrix out, for example, writing out 0 0 0 0 0 0 0 0 0 0 0 0 and 0 0 0 0 0, instead of writing this whole thing, you just simply write O. But you don't specify here whether O is a 4x4 matrix or a 3x4 matrix or a 4x3 matrix, and so on and so forth. But then the order of the matrix is automatically clear from the calculation that you're doing in that particular case. We will know more about these as in the exercises, of course. Now, the next part that we have here is called the equality of matrices, and I think we can do that in this video as well. So about equality of matrices. Now, one thing to remember is that these matrices the concept of matrices is a simple concept in mathematics, and it's usually very popular with students because it doesn't need much thinking, and therefore you can score relatively well with matrices in examinations. And therefore what students usually do is that, for example, instead of studying calculus, they start with matrices, and if they find more time, then they will spend some time on calculus. Otherwise they will simply not do it. And then what they do in the examination, they can of course pick the questions that they can answer, and they pick, for example, the matrix questions and answer those questions, and they pass the test. But as you know, of course, it's a policy that works in examinations. But then when you go to higher levels of education, then of course you're just like you're like a paralyzed person. A paralyzed person, for example, has two hands and one foot, but the other foot is somehow missing. So although you have the two hands and the one foot, but then the third, but it's the second foot is not there, so you cannot walk, right? Now, if the second foot was also there, you could walk to some other places and do a couple of things with your hands. But now you have the two hands, but since you cannot walk, you cannot get anything done because you cannot go anywhere. And this is the kind of mindset that has been developed in our educational system, that basically, of course, students have to come up with these types of policies in order to get those examinations done. Otherwise, it's just not possible, because the amount of material that is given to them is just unbelievably too much, right? And for the same reason, I was never ever successful in any sort of educational system, because, well, it was just not possible for me to do anything, you know. I mean, my goal, of course, was to learn, for example, the things that I wanted, at least the things that I wanted to learn, I wanted to learn them, but there was no time. And as a result, all throughout my life, I've always had to basically get into some educational systems, and then I've always had to, well, get out, because there was no place for me there. But of course, education, of course, is the most important part of anybody's life, and it must be taken care of properly, not in terms of marks, and not in terms of report marks, report cards, and things like that, and not in terms of certificates and things like that. Of course, it's a good idea to have a PhD, but of course, more important than that is to actually understand the material that you read, and give yourself enough time to understand it. Because otherwise it's just some knowledge, some theoretical knowledge, and you wouldn't be able to do anything with that. Or in best cases, it would be some theoretical knowledge that you really don't understand. You have passed some exams, and then after you pass the exam, you will simply forget all of those things. So there is no point in doing that. But at any rate, to me, education is the most important thing that has ever occurred to the human race. And if you want to get it right, you have to do it yourself. Nobody is going to take care of that for you. in my experience, it's never happened. All educational systems have failed in that respect. So that's basically why I'm doing all of this, although I'm not passing any exams or I'm not applying for any certificates or anything like that. But, well, the logic that you have in your mind, that logic has to be right. Your thinking has to be right. Your reasoning has to be right. And logic and thinking and reasoning can only come from education. It can only come from mathematics. There is no other way to do it, as far as we know today. So, yeah, that's the problem today, unfortunately, with our educational systems. Anyway, enough of philosophy. Now about I think I'm going to discuss the equality of matrices in the next video, because this video is already 41 minutes. I'll see you in the next video. Thank you.